Welcome back, students. In the previous lectures we have been looking at applications of matrices, especially on the usage of what is known as the row reduced echelon matrix. In this lecture we will use this row reduced echelon matrix and try to solve a system of linear equations. So, let us begin with. This is the system of linear equation plus a1n xn equal to b1 a12 x1 plus a22 x2 plus up to a2n xn equal to b2 up to am1 x1 plus am2 x2 up to amn xn equal to bm. So, this is a system of m equations with n unknowns, not with in n unknowns, right. So, what we have here is a system of m equations in n unknowns. Now, given a system, how to solve it? Before we proceed further to solving it, here are some of the facts that one will have to observe. So, in fact, there are three possibilities that arise given a system. What are they? First one, no solution. A solution may not exist. You may not be find solutions to x1, x2, xn satisfying the given system. Second, unique solution. And finally, multiple solution. In fact, when you say that it is a multiple solution, it is going to be an infinite solution, infinite set of solution. So, let us try to see how to use this row reduced echelon matrix to solve a given system of equation. So, let us do an example. The given system is minus 3x minus 2y plus 4z equal to 9, 3y minus 2z equal to 5, 4x minus 3y plus 2z equal to 7. Given the system, let us try to write down in the form of matrix: minus 3, minus 2, 4, 0, 3, minus 2, 4, minus 3, 2, and evaluated at x, y, z. What we get is 9, 5, 7, right. So, these 9, 5, 7 they are called the constant terms of the equation, and this matrix that we have here, this is what is known as the coefficient matrix, and this x, y, z are the unknowns. So, this is the coefficient matrix. These are the unknowns and these are the constant terms. Now, given the system, right, we have written down in terms of the matrices. Now, let us try to write down in the form that we needed. So, what we are going to do is write the coefficient matrix and then augment it with the constant term matrix, right, minus 3, minus 2, 4, 0, 3, minus 2, 4, minus 3, 2. We are going to augment this with the constant term matrix. We are going to solve the system by using this augmented matrix. So, first before we try to solve, let us try to convert this into the, let us try to convert the given coefficient matrix into the row reduced echelon matrix. First thing that we will have to do is that find the leading coefficient or the first non-zero coefficient. So, the first non-zero coefficient, the first row is minus 3. So, let us make it into 1. So, what we are going to do is replace R 1 by 1 upon minus 3 times R 1. So, what we will have is 1 2 by 3 minus 4 by 3. Apply the same set of operations on the constant term matrices also. So, you will have minus 3. When you apply minus 1 by 3, you get it as minus 3, 0, 3, minus 2, 5, 4, minus 3, 2, 7. Next thing is to make the other elements of that column into 0, which means we have 1 here. So, the one of them is 0. So, we should convert this 4 into 0. R 3 will replace it by R 3 minus 4 times R 1, 1, 0, 0. So, we will have the same thing 2 by 3 minus 4 by 3, 3 minus 2. We will have to, so we have made this into 0. So, similarly multiply this one 2 by 3 by minus 4. So, you will have minus 8 by 3 minus 3 minus 8 by 3, and similarly 2 plus 16 by 3, you have minus 3, 5, 7 plus 12. And therefore, the resulting matrix that we have over here is 1, 2 by 3 minus 4 by 3 augmented with minus 3, 0, 3, minus 2, 5, 0, minus 17 by 3, 22 by 3, 19. Now, let us look at this submatrix that we have. So, or the leaving the first column and the first row, let us look at the remaining 2 by 2 submatrix. Here again the leading coefficient here, which is 3, it is again non-zero, we will have to make them into 1. So, we will replace R 2 by 1 by 3 times R 2, 1, 2 by 3 minus 4 by 3, and then you will have minus 3, 0, 1, minus 2 by 3, 5 by 3, 0, minus 17 by 3, 22 by 3, and 19. Now, given this, let us convert the other elements of that of the second column into 0. R 1 is replaced by R 1 minus 3 by 2 times R 2. And similarly, for the other one, R 3 is replaced by R 3 plus 3 by 17 times, sorry, it should be 2 by 3, 2 by 3, and here plus 17 by 3 times R 2. Fine. So, what we will have is 1 0 0, and here we are multiplying. So, 2 by 3 minus 2 by 3. So, you have 0 minus 4 by 3 plus 4 by 9, and then here we are augmenting it with minus 3 minus 10 by 3, and then we have 1 minus 2 by 3, 5 by 3, here it is going to be 0, 22 by 3 minus 34 by 9, and finally, we have 19 plus 85 by 9. Fine. Now, let us write down the final matrix that we have. What we have over here is 1 0 0 0 1 0. We have minus 4 by 3 plus 4 by 9. So, the resultant is going to be, what we have is minus 8 by 9 minus 2 by 3, and similarly we have 66 minus 34. 66 minus 34 is going to be 2 3 32 by 9, and similarly for the other one minus 19 by 3, 5 by 3, 181 sorry 171 plus 85. So, you have 6, right, 171 plus 85, 6, 7 plus 8, it is going to be 15, 1. So, 256 upon 9. And finally, we are left with this one. So, let us convert this into 1. So, we are going to replace R 3 by 9 by 32 times R 3. You have 1 0 minus 8 by 9 times 8 by 9 minus 19 by 3, 0 1 minus 2 by 3, 5 by 3, 0 0 1, and then we will have 256 upon 32. Now let us make the other two elements in the third column into zeros. So, we will replace R 1 by 8 by 9 times R 3 plus R 1, and similarly R 2 by 2 by 3 times R 3 plus R 2. What we will end up with here is just the identity matrix, but if you notice on the other end what we will have is just 3, 7 and 8. And so, now let us try to write down the final one in terms of what we have. So, x equal to 3, y equal to 7 and z equal to 8. And so, the final solution that we expect is 3, 7, 8. In fact, this is the solution of the given system. So, the natural question is, given a system of equations, right. So, given a system A x equal to b, so be the given system of linear equations. Now, upon applying the, so let rho be the elementary row operations that are performed on A and B. Now, let me denote by, let A dash or A tilde denote row of A and B tilde denote row of B. Now that I have a new system, what is known as A tilde x equal to B tilde. So, this is the newly obtained system. The given system is A x equal to b, and I have the new system A tilde x equal to B tilde. The only relation that I have is that A is rho equivalent to A tilde, that is, you can obtain A tilde from A just by applying the elementary row operations, and similarly B is rho equivalent to B tilde, right. That is, A tilde is obtained from A just by applying the row elementary operations. Similarly, for B and B tilde, right. So, B tilde is obtained from A B just by applying the row elementary operations. The only thing over here is that the same set of operations that you apply on A are also applied on B. Now, the claim is that A x equal to B, well, the systems A x equal to B and A tilde x equal to B tilde have the same set of solutions. Well, how to prove this fact? One thing that one will have to observe here is the following. Before we go into the proof of this, so let us try to observe some simple properties, that if rho is an elementary, if rho is an elementary row operation, it is just a single operation, then row of A equal to row of I times A. This can be easily observed just by applying all the 3 elementary operations. Just apply it on the A, one can easily verify it at least for a 3 by 3 matrix, although not difficult for a general n by n matrix, but it should be easy for a 3 by 3 matrix. Just apply it on a 3 by 3 matrix A, and similarly apply the same elementary row operation on the identity matrix, multiply it with A, one can notice that these two are one and the same. And because of this, what one can observe immediately is the following. In fact, the following are the consequences. First one is that, well, before I proceed, so let me say that let rho 1, rho 2 up to rho s be a finite set of elementary row operations, right. I have a finite set of row operations, let A be an n by n matrix then you apply all these finite set of elementary row operations one by one on A. Because of the previous one can easily identify that this is going to be same as the same set of row elementary operations first applied on the identity matrix and then multiplied with the just the matrix A, right. So, this is just the matrix multiplication, and here in the first one you are applying these S row elementary operations one by one on the identity matrix and then you are multiplying with the matrix A. Second thing again one can easily observe is that if you are going to apply the same set of row elementary operations one by one on the matrix A, this is going to be same as you apply each and every row elementary operation on the identity matrix in the same order and finally multiply it with E. Well, when you apply rho 1 on A, this is going to be same as rho 1 times identity. So, rho 1 of identity times A. Now, when you are going to apply rho 2 applied on rho 1 identity times A, what you will obtain is rho 1 of identity time rho 2 of identity times rho 1 at A, which is same as rho 1 at identity times A. So, simply by induction one can prove the remaining things, right. With these two things now, a small observation or a note which I will just state here saying that a similar version also holds for n by m matrices also holds for n by m matrices also. First thing that one will have to observe, right. Once you have observed this fact, now one thing that one can easily notice is that an easy thing that again one can notice is that if A and B are any two, if rho is an elementary row operation, and if A and B are any two matrices which can be multiplied then a simple thing that one can observe is the following. What is that? Rho of A B is equal to rho A times B. Well, how does this follow? Just use the previous one. Rho A times B, sorry, rho of A B, this is going to be same as rho of identity times A B, but rho of identity it is again a matrix and we know that matrix multiplication is associative. So, let us use all these things, rho of A B which is equal to rho of identity times A B, but use the fact that the matrix multiplication is associative and rho of I is just a matrix. So, this is rho of I times A and then you multiply this with the matrix B which is same as, but rho of I times A, this is just rho A times B, and therefore, if rho S minus 1, rho 2 rho 1 is a finite set of elementary row operations, then the same conclusion as what we said earlier, rho S composed with rho S minus 1 composed with rho S minus 2, rho 2 composed with rho 1. If it acts on, if these elementary row operations, if it acts on A B, this is going to be same as rho S composed with rho S minus 1, rho S minus 2 up to rho 2 rho 1, just let it act on A, this matrix just multiplied with S. Once we have this, now one can easily show that these two will have the same solution. How is it possible to show that? So, A x equal to B is the given system. Now, suppose x is the solution to the system, in fact above system, then rho of A x is equal to rho of B, where rho is any elementary row operation. We have this, and therefore, once we have this, but use the previous one, this is equivalent to saying that rho of A times x equal to rho of B. So, in the previous notation just we used just few minutes back, this is same as A tilde x equal to B tilde. That is, the solution x what we had for the system A x equal to B is also the solution for the system A tilde x equal to B tilde. Now, use the fact that the elementary row operations are invertible, and therefore, what we have is that if x is the solution for this system A tilde x equal to B tilde, then x is also the solution for the system A x equal to B. So, what we just did is only for the just one elementary row operation, and now we know that a similar thing holds even for a finite sequence of elementary row operations when applied altogether, and therefore, the system A x equal to b and the system A tilde x equal to b tilde have the same solution, right. So, whatever we have said, thus the systems A x equal to b and A tilde x equal to b tilde have the same set of solutions if A tilde is obtained, sorry, if A tilde and b tilde are obtained from A and B respectively just by applying a finite set of elementary row operations. Right, just by applying a finite set of row operations, one can obtain a new system A tilde x equal to b tilde. We just concluded is that the system A x equal to b and the system A tilde x equal to b tilde have the same set of solutions. Now, let us do one more problem. 2x minus 3y equal to minus 21, 3x plus 2y equal to 1, 8x minus 5y equal to minus 49. One can notice that this is an overdetermined set of equations, overdetermined system, right. This is an overdetermined system. Why do we call it as an overdetermined system? Because what we have is just only two variables x and y, but we have three equations. Now, let us try to solve this system. Let us first write the augmented matrix, or before that let us first write the matrix form 2 minus 3, 3, 2, 8 minus 5 evaluated at x y should give us minus 21, 1 and minus 14. This is the system that we have. Now, let us try to write down the augmented matrix 2, 3, 8 minus 3, 2 minus 5. Let us augment it with the constant term matrix minus 21, 1 minus 49. This is the given augmented matrix, or this is the system, and we have given system we have write down in the as the augmented matrix. First thing that we will have to do is that look for the leading coefficient. So, this is the leading coefficient and we will have to convert it into 1. So, let us do that. R 1 is replaced by R 1 1 by 2 times R 1. So, what we will have is 1 minus 3 by 2, we are augmenting it with minus 21 by 2. So, let us have the other things as it is 3, 2, 1, 8 minus 5 minus 49. So, the next thing that we will have to do is that convert the remaining elements of the first column into 0, replace R 2 by R 2 minus 3 times R 1, and similarly replace R 3 by R 3 minus 8 times R 2 R 1, 1 minus 3 by 2, let us augment it with minus 21 by 2, first one. Second one we have 0 and again 0 here. What we will have is 2 minus, so plus 9 by 2, 1 plus 3 times of this, which is 63 by 2, and again minus 5, we are multiplying this with 8 plus 24 by 2, and here you will have minus 49 plus 21 into 8, 162 by. Now let us try to write down the final one. So the matrix that we finally obtain here in the stage is 1 0 0 minus 3 by 2, 13 by 2, 14 by 2, augmented with minus 21 by 2, 65 by 2, 81, 150, sorry 130, yes, because 162 by 2 which is 81, 81 minus 49, okay, 81 minus 49, which will give us 11 minus 9, which is 12, 7 minus 4 3, so we will have 32. We will have 32. Now the next one that we will have to look at is this term, which we will have to convert it into 0. If you start so what we will have to, for you this we will have to convert into 1, R 2 should be replaced by 2 by 13 times R 2, 1 0 0 minus 3 by 2 will have 1. So the remaining rows are untouched. You have 21 by 2, which is 5, 32. I will have to convert the other things into 0. So what I will do is R 1 is replaced by 3 by 2 times R 2 plus R 1, and similarly R 3 is replaced by minus 14 by 2 times R 2 plus R 3. What will I have? 1 0 0 0 1 0 and then I will have to work out here minus 21 by 2, right, 5 into 3 by 2, which is 15 by 2, minus 21 by 2, and similarly I will have 5 here, and the last one 32 minus 70 by 2, which is 35. Yes, this should be 35 exactly. Yes, this should be 35. Yeah, so in the previous one this should be 168, so that you get it as 84 plus 3. So this is going to be 35. Yes. So the final resulting matrix that we have is, this is the final resulting matrix 1 0 0 1 0 0, and then what you will have is minus 3 5 0. So now let us write down the final set of equations: x equal to minus 3, y equal to 5, and z equal to, sorry, there is no z, sorry, right. So this is the solution to this system. Now, if you notice this one, the last row completely turns out to be 0. Now, if at all there is a system, in which when you reduce the A matrix to its row echelon form, row reduced echelon form, and if the last row turns out to be 0, but if you apply the same set of row elementary operations on the constant matrix and notice that the last term or the whatever be the wherever the zeros are there, and if you obtain a non-zero term, then one can easily conclude that such a system has no solution. Or let us just make a note in terms of rank. A system of linear equations has a solution if rank of the given matrix or the coefficient matrix A is equal to the rank of the matrix A augmented with B, the constant matrix B. If these two, the ranks of these two matrices, if they coincide, then you say that such a system has got a solution. If they does not possess, then we say that such a system has got no solution. Now, let us do one more example. 2x minus 3y plus 2z equal to 13, 3x plus y minus z equal to 2, 3x minus 4y minus 3z equal to 1. This is the given system. Now, first let us try to write down the matrix form of this: 2 minus 3, 2, 3, 1 minus 1, 3 minus 4 minus 3. When applied on the system, when applied on the unknown x, y, z, should give me 13, 2 and 1. Now, first as usual let us write down the augmented matrix: 2, 3, 3, minus 3, 1 minus 4, 2 minus 1 minus 3, augmented with 13, 2, 1. The coefficient matrix, when we adjoin the constant term matrix along with the coefficient matrix, we call it as the augmented matrix. We first look for the non-zero rows, and there are no non-zero rows in this case, and therefore, what we find is we will look for the first non-zero coefficient, the first row, which is going to be just 2. We convert it into 1. R1 is replaced by R1 1 by 2 times R1 1, the remaining rows are untouched, minus 3 by 2 1, 1 minus 1 minus 4 minus 3, and then here it is minus 13 by 2 2 1. Now, we will have to convert the other elements of the first column into 0. Let us do that. We will replace R1 by R1 plus 3 by 2 times R2 and R3 by R3 minus half times R2. So, what we will have? So, the first column will have 1 0 0, second column again will have 0 1 0. Now, let us compute the third one R1, which is 1 plus 3 by 2. So, which is we will have minus 8 by minus so we will have 12 by 11, second row remains unchanged minus 8 by 11, third row R3 minus 6 plus minus half times 8 by 11. So, plus 4 by 11 augmented with the last column 13 by 2 plus 3 by 2 times minus 35 by 11. So, you will have, so minus 105 upon 11. Second row, the second one remains unchanged. Third one minus 37 by 2 plus 35 by 22. So, the resulting matrix in this case is 1 0 0 0 1 0 1 minus 12 by 11. So, you have minus 1 by 11, minus 8 by 11 second one, minus 24 minus 66 plus 4 by 11 plus 4. So, you will have minus 62 by 11, the last column. You will have 13 into 11, which is 143, minus 105. So, you will have it as 38 by 11, sorry, minus 38 by 22. Second one remains unchanged, it is just this one. The last one which you will have is 37 into 11, which is 407. So, 407 plus minus 407 plus 35, which will give you 372. So, this is going to give you 372 upon 11, sorry, upon 22. So, the last element here, that is the minus 62 by 11, we will convert this into 1. So, R 3 is replaced by 11 minus 11 by 62 into R 3. So, what we will have here is 1 0 0 0 1 0 minus 1 by 11 minus 8 by 11 1, the last column 38 by 22 minus 35 by 11, and here you will have this is going to give me minus 372 and minus 60 upon minus 62, that will give me just 6, and 11 by 22 will give me half. So, I will have just 3. So, what we will have to do now is convert this minus 1 by 11 and minus 8 by 11 into 1, sorry, into zeros. So, let us do that now. R 1 is replaced by R 1 plus 1 by 11 times R 3, and similarly R 2 is replaced by R 2 plus 8 by 11 times R 3. Let us compute it. The first and second columns, they remain unchanged, 1 0 0 0 1 0, and based on these computations it is again clear that the last column is again 0 0 1. Let us compute the final column, which is the augmented one. What we will have is R 1 38 by 22 plus 1 by 11 times R 3, which is 3 by 11. The second one R 2, so minus 35 by 11 plus 8 by 11 times R 3, so which is 24 by 11, and the last term is just 3. So, the resulting matrix here is 1 0 0 0 1 0 0 0 1. So, 38 plus 6, which will give me 44, 44 by 22 will just give me 2. The other one minus 35 plus 24, which is just minus 11 upon 11. So, I will have just 1, and the last one is just 3. Therefore, the solution is 2 minus 1 3 is the required solution. With this, let us stop this lecture. In the next lecture, we will see some more examples on solving system of linear equations, especially on those systems which have no solution and which possess infinite number of solutions. Thank you all.